We present FlowHOI, a flow-based semantics-grounded hand-object interaction generation framework for Dexterous robot manipulation. FlowHOI is the first framework to model human-object interaction generation as a unified, conditional flow matching process grounded in semantic understanding. Given a real-world scenario, it produces physically plausible and semantically consistent interaction trajectories that can be directly deployed for dexterous hand manipulation. Given initial observation, action description and a reconstructed 3D Gaussian splatting scene, our method generates a temporally coherent HOI sequence in two stages. First, a grasping stage, which focuses on geometry and reachability. It produces a stable approach and grasp motion using a pre-trained grasping prior. Second, a manipulation stage, which generates long horizon interaction motions conditioned on scene tokens and language instructions. This stage ensures that object state changes are consistent with both the physical layout and the task semantics. By decoupling geometry-centric grasping from semantics-centric manipulation, our framework maintains contact stability while preserving semantic alignment. We evaluate the generated hand-object trajectories on the GRAB and HOT3D datasets. Compared with state-of-the-art methods, FlowHOI achieves superior geometric consistency and stronger text alignment performance. In our ablation study, we first show that leveraging a pre-trained grasping prior leads to significantly more stable grasps. We further demonstrate that introducing the text alignment loss ensures that the generated motion strictly follows the command. Without it, the motion often ignores detailed descriptions in the text, such as which hand should perform the main action. Benefiting from our fused semantic and geometric scene conditioning, the generated motions are more consistent with the surrounding scene and better reflect the intended manipulation. To validate the effectiveness of the generated trajectories, we retarget them to the Allegro hand using inverse kinematics and evaluate them in physics simulation to verify the physical feasibility. We show that our model achieves the highest success rate and the longest object holding time in simulation. At the same time, it is up to 40 times faster than diffusion-based baselines, requiring only 0.16 seconds for inference per sequence. Finally, we designed several real-world manipulation tasks to transfer our generated motions to a real robot, demonstrating successful execution in contact-rich scenarios.